Okay, so first of all, I would like to thank the organizing committee, Professor Patra, Professor Chen, Professor Antoine, as well as the team of the PhD students who are taking care very efficiently of the logistics. And I would like also to thank the CEFIPRA, the Indian French committee, who provided the money, a significant amount of money for this symposium to exist. So I am an applied theoretical chemist. I am interested in rationalizing stability, structure, bonding, and properties of clusters. And today I'm going to talk about silver-rich and copper-rich clusters. So here's my outline. I will make an introduction, a rather long introduction, to define what is a superatom from the point of view from the orbital point of view. And then I will describe some silver-rich and a few copper-rich systems. Then I will talk about assemblies of superatoms, which I call supermolecules, or some people call them superatomic molecules. Then I will shift to systems which contain hydrogen encapsulated within the core of the cluster, and then a conclusion. So what is a superatom? Before starting talking about a superatom, let me remind you something that anyone in this room knows very well. This is the electronic structure of a polyelectronic atom. So this is the Hamiltonian of a polyelectronic atom in atomic units. I would like to focus on this part of this operator, which is the potential describing the interaction between the electrons and the nucleus. This is, of course, the system is of spherical symmetry, so this potential is spherical. It's a radial potential. It depends only on the distance of each individual electron and the nucleus. We know that the solution of the Schrödinger equation is a polyelectronic wave function, but we usually express it on the basis of one electron wave function, one electron functions, which we call atomic orbitals, which are the product of a radial function and an angular function, which is a spherical harmonics. And these atomic orbitals, they have a level ordering which is more or less constant over the whole periodic table. And we know that an atomic system, an atom or an ion, is stable when it's a closed shell, when it has the configuration of a rare gas, 2 electrons, 10 electrons, and so on, helium, neon, argon, krypton, and so on. And these are the number of electrons which provide a stability to an atomic system. Now, let's go from an atom to a molecule. What is changing, of course, we have now several nuclei. So we have a sum not only on the electrons, but also on the nuclei, and we lose the spherical symmetry. But let's consider a spherical or almost spherical molecule. If this spherical molecule is also a compact, is made of metal atoms, for example, which are associated in a compact way, then we can make an approximation which is called the spherical Jellium approximation. The cloud of the point charge associated to the cloud of nuclei, the compact cloud and spherical cloud of nuclei, we can express it. It's an approximation. We can average it. And then if we average it, it will have also a radial form. It will be a radial potential. It's different from this one, of course. This is so let's see, a rounded U shape with a value inside the sphere and another value outside the sphere. And then these two expressions are related. They are not similar, but they are related. And actually, we can express the solution of the Schrödinger equation based on this approximate Hamiltonian as a polyelectronic functions which can be expressed on the basis of one electron function that we will call superatomic orbitals, and which are also the product of a radial function and a spherical harmonics. We don't have this potential is radial as well, like this one, but they are not the same. And it turns out that we don't have any condition on the n on L quantum numbers. So we can have 1p, 2p, 1d, 2d, 3d, 1f, 2f, 3f orbitals. That's one difference. We have also an energy level ordering which is almost constant among families of compounds. And for the same reason as for a polyelectronic atom, it will be chemically stable when any of these shells, 1s or 1p or 1d or 2s and so on, is filled. So we will have also closed shell electron count, which correspond to number of electrons, favored number of electrons in terms of stability. People call them magic. They are not magic, but this is their name. So to summarize, a level ordering and various magic number of electrons, which correspond to closed shell situation. Just, I would like to mention that the spherical Gellium model, the superatom model, is a qualitative model. We don't use it to make calculations. The calculations are made usually by DFT calculations. And so DFT calculation, I mean, these electrons are the electrons which are associated with metal-metal bonding within the sphere. When you consider a molecule, you have ligands and so on. So DFT calculates all the orbitals, all the electrons, and we have to identify among the molecular orbitals, the cone-sham orbitals, we have to identify those which can be considered as the superatomic orbitals. So just a few examples. Now let's focus to group 11 systems, copper, silver, and gold. So these copper, silver, and gold have the d shell completely filled. Gold is 5d10. So the d electrons do not participate in first approximation to the bonding. The orbitals which participate to the bonding are the 6s orbitals, and the electrons which they contain. So we have to count. These are the superatomic electrons, are those coming from the 6s orbitals. So let's look at some examples, which I have taken from this very nice paper from Akinen. Gold 13, so it means that if gold was 0, we would have 13 electrons, but we have 2 chloride oxidation state -1 to chloride atoms, so -2, and we have a +3 charge, so -3. So the result is 8 with this configuration. Looking at this one, for example, thiolates is formally -1, so we have 102 atoms of gold, so 102 minus 44, 58, and we have this closed shell configuration and so on. So let's start with a real compound on which we calculated. This compound was made by a group of experimentalists in Taiwan, the group of Professor Shenwei Liu in National Donghua University in Taiwan, with whom we collaborate. So we started looking at this compound, 21 silver atoms, 12 ditiophosphate ligands. These ditiophosphate ligands are formally -1. Looking at the electronic structure and the molecular structure allow us to divide the 21 silver atoms in 2 categories, the pink ones and the green ones. The pink ones are making a silver 13 centered icosidron. A centered icosidron is something very compact, almost as compact as FCC or SCP. and green atoms. And actually, we have a system which contains a superatomic core, silver 13 5+, 8 electron, and which is protected, which is, people say, passivated by 12 ligands, formally -1, and 8 silver 1. It's a closed shell. We can go a little bit further on the structure. This is the electronic structure of the core, silver 13 3+, in icosidral symmetry. This is the D band, which is roughly non-bonding, but we have also the 1s orbital, which is there, and which looks the 1s orbital of an atom, but this time it's expanded over the whole sphere of the cluster. The HOMO is triply degenerate, and this is a 1p HOMO. You see py, px, pz, and the LUMOs are the 1D LUMOs, which are there. If you go to the full cluster with the protecting shell, slightly modelized, but it doesn't matter for the purpose. We have, of course, a lowering of symmetry, so the degeneracy is no more there. Degenerate splitting, but it doesn't matter. We can recognize the 1p levels. We can recognize the 1d levels also. So just to summarize, this compound, it can be divided in two parts. The real superatomic part of the superatom, so speaking, which is the core, silver 13 formally 5+, and the protecting shell, which is made of 12 dithiophosphate ligands and 8 silver 1. And if you look at the green atoms of silver 1 in the +1 oxidation state, they are in trigonal planar coordination. So they are happy. They are happy as they are. They are stable locally, 16 electron center, planar 16 electron center. They are not going to seek for additional bonding. And actually, their bonding with the pink atoms is mainly metallophilic in character. The covalent character is very weak. And it turns out that it's possible to change, to alloy these systems and change the metal in the center by gold, platinum, palladium. We know it will go in the center, and we have an orbital explanation for all the metals which are on the left side of the periodic table. They will go in the middle. Copper will not go in the middle. So we have a large family now of compounds of this type with different M, but we can change the sulfur into selenium also, and even we can play with R. And it turns out that the group in Taiwan has reported 5 structures which are commonly observed, 5 different structures, which differ only by the topology of the protecting shell. There are 5 different topologies of the protecting shell which have been observed. In all these protecting shell, the metal, the green silver 1 metals are planar trigonally coordinated. And DFT shows that the 5 structures are very close in energy, irrespective of the value, irrespective of the nature of M and E. So this structural diversity combined with allows tuning the optical property within this family of compounds. I'm not going to discuss this, but it's something that we are looking at. So here are the 5 structures. The ligands are not shown. This is a C3 structure I showed previously. There is a T structure and 3 different C1 structure. With some example, my fingers are too big. So these are only a few examples, actually. There are more. Just to show you, the homometallic system with 21 silver atoms, the 5 structures lie within the range of 5 kcal per mole, approximately. In the case of the platinum-centered, they lie within the range of something like 2 kcal per moles. 2 kcal per moles is not significantly different from 0 at our level of theory and modelization, actually. I just would like to mention this copper system, which was made in the same group of Professor Liu. 13 copper atoms, which are making a centered cube octahedron. The cube octahedron is slightly less compact than the icosahedron, and it is likely induced by the nature of the dithiocarbamate ligands, which like to coordinate square faces. We have several square faces. So we have 6 DTC dithiocarbamate formally minus, 4 formally minus CCR ligands. Then we have a copper 13 formally 11 plus, which means it's a 2-electron system, and this is proven by the calculation. We have the 1s2 orbital, which is the HOMO, which is there, and the LUMOs are the 1p orbitals. I will come back to this structure at the very last end of my talk. I would like to shift to assemblies of superatoms. our colleagues in Taiwan, they isolated 3 different compounds from the same reaction. This one is a regular 8-electron system. This one is made of 2 edge-sharing, vertex-sharing icosahedra, 16 electrons. 16 is 2 times 8. So one superatom and another superatom interacting weakly. The interaction is negligible, so it's not very interesting. This one is much more interesting. We have 3 vertex-sharing icosahedra, but 22 electrons. 22 is not 3 times 8. It's 3 times 8 minus 2. So we started looking at these systems in the way people look assemblies of atoms as molecules. So, for example, if you look at diatomic molecules, very simple, N2O2F2, neon 2, which is a van der Waals molecule. So let's suppose it's a van der Waals molecule. So each time you are making a bond, you are removing 2 electrons, 1 bond, another bond, another bond. So we go from 16 to 10, like that. It depends on the bond. The electron count depends on the bond order, and I will say on the compacity later. So the question is, can we make the same thing with 2 icosahedral superatoms and make molecules which are isoelectronic, isolable, equivalent to superatomic molecules? Actually, the answer is already in the literature. There is this very nice paper from Mingos in 2015. These 2 guys have developed more or less similar approaches. So Mingos said, looked at the literature and was able to find examples. These are only picked examples. This one, vertex sharing 16 electrons, so it's isolable. It's equivalent to van der Waals molecule, neon 2, no bond, no interaction, no significant interaction between the 2 icosahedra. When you increase the compacity, phase sharing now, you can have 14 electrons, this system, equivalent to F2. And when they are interpenetrating means that the 2 icosahedra are sharing the red atoms and the green atoms, then you can have 10 electrons, compacity increased. So the question is, how about 3 icosahedra? And actually, we did the calculation of this compound. Here is the MO level ordering of the core. We got rid first of the protecting shell. Here is the core. Here is I3 minus. And actually, there is a 1-by-1 correspondence between the orbitals of I3 minus and the core of these systems. When you calculate the whole cluster with its protecting shell, the symmetry is reduced is highly reduced, of course, but we have the same correspondence, believe me. So the 1s and 1p genome orbitals of the 3 icosahedra combine similarly as the 5s and 5p atomic orbitals of iodine in I3 minus with the same number of electrons. So it made us to think that maybe there are other systems that we could predict in the literature. If we look at 3 atoms, CO2, it's linear, bond order 2, SO2, it's bent, bond order 1.5, SF2, it's bent also, bond order 1, 20 electrons. I3 minus, I just talked about it. The bond order is 0.5. And let's say 3 neon atoms in a van der Waals interactions. So what we did, we calculated only the cores, the cationic cores, and we looked for the best electron counts of these systems in looking at HOMO-LUMO gaps mainly. So I just talk about this one. We have an electron count, 2 favored electron count. Actually, I didn't show that, but you see, 22 electrons, we have a large electron gap, but if we add 2 electrons, we are also going to have another gap. So there are two favored electron counts, and actually, I just show that there is a real example, but with 24 electrons also, there are some examples in the literature. More compact, phase sharing, linear, 22 electrons. It would correspond to A3 minus. No examples in the literature so far. Phase sharing, but bent now, 20 electrons, equivalent to SF2. No, it's a prediction so far. Interpenetrating, three interpenetrating icosahedra, 16 electrons, equivalent to Ca2, and there is at least one example in the literature. We can make a triangular system, vertex sharing, well, it's 24 electrons. But if it's fast sharing, then the electron count is 18, favored electron count. It corresponds to the hypothetical high-energy isomer of ozone, triangular O3. We can do the same with 4 icosahedra. This is what we did. I'm going just to mention one case, just starting from this molecule and adding another one, repeat motif, and modelizing the outer shell similarly. We got this system, and we looked for the best electron count, for the best charge, actually. And we found it is -2. -2 corresponds to 30 electrons, and it's isolobal, isoelectronic, equivalent to the I4 ion, which is linear. Here are the two lemmas. Actually, our colleagues in Taiwan are still trying to isolate it. Probably they made it, but in a very, very low yield. Later, after we predicted this electron count, it was confirmed by a work from Quanming Wang, a Chinese group, where they made a 30 electron system, which is made of four linearly arranged vertex sharing icosahedra with different ligands and different outer shell, but the same core. Now I would like to shift to something which we are interested at the present time, still made in the group of Liu. These two compounds, this is sulfur, this is selenium, this is C1, this is C3, two different protecting shells, and there is a neutron diffraction structure. But what is interesting is that they contain, a nitrogen encapsulated within the icosahedron. Actually, the hydrogen is strongly bonded to platinum, which is at the center, and weakly to the copper atoms. If we want to get the 8 electron count, and I will tell you this is what we have to do, we have to count the electron coming from the hydrogen atom in the sum to get 8 electrons, because platinum is a 0 electron donor, hydrogen 1, 19 silver atoms, -12 minus the charge of the formal charge of the ligand equal 8. To understand this, let's look at these two. These are optimized structure, DFT optimized structure. There is no outer shell, but if we consider some outer shell, we get the same results. So let's look at the core. Let's look at this one first. We have a hydride ligand. It's +3. We have a hydride ligand, which is a ligand. It behaves as a chlorine ligand, for example. So we have a formally 4+8 electron cluster, which has an outer shell, so speaking, made of one H- ligand, and the charge is +3. If we remove 2 electrons from this system, then the structure will evolve to this one, in which the hydrogen is incorporated inside, and now we have to count the electron of the hydrogen to reach the 8 electron system. So this is this case I'm going to comment. So let's start with this system. Let's formally remove the hydrogen atom first. If we remove the hydrogen atom, in the center we have a platinum atom, and the platinum atom will use its 6s orbital to build the supermolecular orbitals. The supermolecular orbitals are made of these 6s orbital. This is okay, but one electron is missing. If we had gold in the place of platinum, we would have 1 electron there, and now we would have a count of 8 electrons. If we add these hydrogen atoms here, it will bind mainly to platinum, and the 1s orbital will interact with the DZ2 orbital of platinum, making a sigma bonding orbital, low-lying, and high-lying sigma star PTH orbital. The 6s orbital of platinum is not that much involved in the interaction. We can consider roughly it remains the same. What is changing? So it is still ready for interacting with the other s orbitals of the silver atoms to make superatomic orbitals. But now we have one more electrons because the hydrogen has given one electron. And now we have a PTH unit which, from the superatomic point of view, is equivalent to a gold atom, to PT minus, to a gold atom. And then we have the right number of electrons. This electron is there, and the count is 8. So the electron participates in the superatomic electron count, but the 1s atomic orbital does not contribute significantly to the building of the superatomic orbitals. The hydrogen is there to provide its electron to platinum. This is exemplified by these three MO diagrams. We have the hydrogen encapsulated species over there, and on both sides we have related systems which are isoelectronic but don't have any encapsulated hydrogen. They have the same electronic structure basically. The only difference is that this compound has a low-lying sigma PTH bonding molecular orbital, which is mainly made of DZ2-PT of a DZ2-PT contribution. Quickly, more recently, the group of Professor Liu was able to make this very nice series of compounds. This is rhodium now. And the number of green peripheral silver atoms is changing, decreasing, and the number of hydride is increasing 0, 1, 2 hydrides, and the three compounds have 8 electrons. And this is the same story. I'm not going to discuss in detail, but this is the same story. We have the same frontier orbitals for the three systems, 0, 1, 2 hydrogen atoms. You can see that the frontier orbitals, which are the 1p and 1d levels, they have, in the case of the hydrogen-containing system, they have very little participation of, this is a third number, very little participation of the hydrogen atoms. The hydrogen atoms are basically here just to provide electrons and to complete to 8. They provide the electrons to the platinum atom. Now, to the rhodium atom, sorry. Now, I would like to shift to a very interesting system. So I said this is my last transparency. I said that I presented a centered cuboctahedral system in one of my first slides. Here we have also a cuboctahedron. This is platinum inside. We have a hydrogen encapsulated, which is there. But we have one missing vertex on the cuboctahedron. Actually, it's a 2-electron system, and it can be considered as a superatom, even if it's not very spherical, so speaking. This is this compound. On the other side, we have an isoelectronic compound with a completed cuboctahedron. They have the same electronic structure, more or less the same 1s HOMO. These two compounds can be said as the Closio and the Nido related systems in the way for the people who knows about Borane clusters or organometallic Wedmingos clusters. This is the same. They have the same number of skeletal electrons, of cluster electrons, and they only differ by the number of occupied vertices. What is interesting with this compound is that it's a very good electrocatalyst in hydrogen evolution reaction. Very good, actually. And so we could think that the hydride is involved in the catalytic cycle, but it does not actually. From DFT, it's clear that it is there only. It is not exchanged. It is there only to provide stability to the system. His role is to maintain the stability of the structure, and especially of this cavity there, because during the catalytic process, the hydrogen is entering this way, bonding to the palladium atom mainly, and the second hydrogen comes in and H2 is made. So just to conclude, it's a very general conclusion. I hope having convinced you that computational investigation are necessary, or at least very, very useful for rationalizing stability, structure, and bonding of superatomic cluster. They are also very useful for rationalizing their properties. I didn't talk about properties because I didn't have time, but we are interested in optical properties, chemical and dynamical properties, especially in the case of the hydride-containing clusters I just discussed. We are mainly interested in the relationships between structure and properties, and rationalizing this relationship within families of compounds. They're also useful for predicting new architecture and helping experimentalists to design to improve the property they are interested in modifying their clusters. So people who participated at this work, my colleague, Dr. Samia Kalal, actually we are working together, so speaking, and some former postdocs, former PhDs, and one PhD. All the compounds I presented you were made in the group of Professor Shenwei Liu, National Donghua University in Taiwan, and his group, of course. We have a very strong collaboration together. We are working in close, in intricate synergy, I would say. These are the funds providers, and thank you for your attention.
Thank you.
Impressive talk, impressive result. Thank you. I have a question. You mentioned at a given time that we can easily, or we can recognize the orbitals, the P and D orbitals in the nanoclusters. I know molecular orbitals, so I agree with you. But when you look at in details and you compare the orbitals, there are some differences. So my question is, where are electrons in these superatoms? I mean, you have molecular orbitals, which is a kind of density or related to density, but you cannot localize electron because you have some delocalized electron and partly localized electrons. So did you look at natural bond orbitals or molecular charge to see if you can discriminate or have more insight into the nature of charge?
Actually, it's not so difficult to, in most of the cases, at least for the systems that I have talked about, it's not so difficult to organize, to identify these orbitals just by looking in details at the Kohn-Sham molecular orbital composition and so on. Yes, of course, we are doing also analysis of charges, localized orbital and so on. Yeah. But in most of the cases, the orbitals which are important are when you have an 8-electron system, for example, the orbitals which are the most important are the 1p, which are the HOMOs in general, or close to the HOMOs, and the 1d, which are the LUMOs. So these orbitals are very easy to identify in these systems.
Yes, please. Thank you very much for this wonderful and very pedagogical talk. I have a question about the interpretation of the things. When you, I agree totally with what you say about the superatoms and so on. When you then say, if you compare this with atoms that make bonds and thus produce molecules, the atoms themselves would not change really a lot, but it's the electrons who would make these bonds and create a new system, the molecule. So in what you show here, which is beautiful, in most of the cases you also had the structures touching. You even went a step back to say, well, I first connect the cores without the ligand shell and see what is happening, and then I go back and calculate the superatom states. So my question is, what is really making the bonds between these different structures? Are there clear cases when you have the superatom states that come from each one of the two clusters make the bonds that hold the new molecule together, or is this always a hybridization?
Yeah. This is a very important point. I didn't discuss it because it takes some time to explain. But in molecules, you have bonds. I made a comparison between these bonds and the capacity of the supermolecule. We don't have. I mean, you can identify pi star, sigma star orbitals also in supermolecules. It's quite easy actually, at least in simple systems. But these are not. I mean, the comparison that you can make is the same nodal properties. So the pi star or sigma orbital in a supermolecule will have the same nodal properties as a sigma star or pi star molecule. But bonds, actually there are no bonds. It's just a matter of capacity. But there are no bonds. No.
Okay.
You understand? Do you?
I think so. Yeah.
It's just a matter of nodal properties.
I have two small questions. The first one is from your collaborators. Do they get some single crystal from all the compound?
Yeah, all the compound, all the experimental compound I showed, there is an X-ray structure.
Okay.
Or a neutron structure for the hydrides.
And the second question, you show some superatoms when you say that without the passivation layer. Is it because it's very complicated? Or do you see for you the next step of trying to modeling this kind of superatom?
We did some, but it's very expensive in computing time. And for qualitative explanations, we don't need them. We have, from my experience, I can tell you we don't need them. For electron counting purpose, we don't need them. Okay? And electron counting is just something based on very qualitative arguments.
Okay. And maybe my last question, it's maybe a naive question, but you had this work when they show that depending on the size of the core, it will affect the staple and the rigidity of the small dimer, trimer. Is it something like you see in all kind of system you try to modeling, or it's very specific?
I'm not sure understanding.
It's when you have the staples, they were explaining for some kind of, I think it was the work of Feng Xiaoyin, that depending if you have 4 gold atoms or 2 gold atoms making these staples, it affects the rigidity of stabilizing the core. And basically, if you're working with a 25, with a 13 kernels or with a bigger one, it affects. So does this effect is the same independently of the structures of your?
I don't think it's. I mean, I didn't say that.
No, I'm asking.
You're asking. Yeah. No, it depends what you are looking at. Okay, if you are looking at something very sensitive, I don't know, vibrational properties, for example, yes. But if you are looking at general trends in structural chemistry, no.
Okay. Thank you. Any other? Yes.
Yeah. Thank you for this very nice talk. You mentioned that you have van der Waals interactions between superatoms. You're doing DFT calculations. How do you account for the correlation?
No, I didn't say that. I'm sorry, I was not clear enough, probably. I said that, for example, if you have a system with 2 vertex-sharing icosahedra with 2 times 8 electrons, 16 electrons, then you have something which is equivalent to a van der Waals neon 2 molecule. This is what I said. But of course, there is no the two superatoms are sharing a vertex there, so they are linked. They are chemically linked.
Okay. And is there any correlation between the 2 superatoms electrons?
There is very little communication, electronic communication between both. This is when you have less than n types 8 electrons that you have communication. So this is why we are interested in the linear systems, linear vertex sharing systems, because with a number of electrons lower than n times 8, you have communication. You can have communication between both ends, electronic communication.
Okay, thank you.
Yeah, maybe.
It reminds me the nice review of Walter Eyre on the Gelium model, and I remember that for ellipsoid clusters, they were adjusting this Gelium model and find new magic numbers. I was wondering if this system where you have communication with electrons towards these clusters would be simply explained by ellipsoid model.
No, the answer is no. But you're right. There are some superatomic systems which can be described as Jahn-Teller distorted spheres. So they have because of level splitting, they have different electron counts. But these no, because you need compacity, and when you have two icosahedra sharing a vertex, each icosahedron is compact, but the whole structure is not.
Long live India and France friendship.